In this video, I'd like to start talking about Chapter 13. The topic of Chapter 13 is Statistical Thermodynamics. And this is a very interesting topic. And we've seen a little bit of it earlier when we were talking about multiplicity of states back in Chapter 3. And so that introduction will be useful to what we're going to do now. And back in Chapter 3, I mentioned that there was a fundamental assumption. And I'm going to write that fundamental assumption down again. And here it is. The fundamental assumption is that all microstates are equally likely, meaning there is no preference for one microstate over another as far as nature is concerned. Now, from this fundamental assumption, it's really amazing how far you can go. And the topic of statistical thermodynamics is to show that starting with this assumption, that all of thermodynamics arises from probability. So thermodynamics is probability applied to the random motions of the microscopic world, which I probably should say molecular or atomic world to be a little bit more accurate here. Okay, so that's the idea behind statistical thermodynamics. Okay, we're going to start with some terminology in 13A, including some that you've seen before. The first term I want to talk about is configuration of a system. And this is what before we basically were referring to as a microstate. And here's how your textbook likes to write down a configuration. So a configuration looks like this. It is a sequence of numbers, n0, n1, n2, and so on, where n0 is the number of molecules in state 0, which would be the ground state, typically. N1 is the number in state 1, and so on. N2 is the number in state 2. And we're going to extend this notation a little bit and say that that state 0 is the state where the energy is what we'll call E0. Okay, so this is the energy of state 0. This one is E1 or epsilon 1. This one is epsilon 2, and so on. And then if we add all of these numbers up, we should get the total number of molecules in the system. So the total number of molecules, N, is equal to the sum of all of these, which we'll call N sub I, the sum over I of all the N sub I. Okay, the next term we need to define is multiplicity, which we saw back in section 3A. You can find that discussion on page 33 of these notes. But the multiplicity is, oh, and your book calls this the weight. I called it the multiplicity. The book calls it weight. And the multiplicity is equal to the number of microstates. So the number of ways you can arrange the microscopic configuration, that number of microstates that correspond to a macrostate, whatever macrostate we are asking about. So we calculated multiplicity back in chapter 3 for a few different cases. We did it for coin flipping. We did it for a deck of cards. We did it for two solids that were in contact with each other using Einstein's model of a solid. So we've seen this a few times, but in this chapter, what we're going to do is we're going to talk about the multiplicity of a configuration, microstate, that is written like this, where we have N molecules with a certain number in the ground state, a certain number in the first excited state, second excited state, and so on. So what's the multiplicity of a configuration that looks like this. That's going to be what we're going to figure out next. And I think it's easiest to see this if we work from an example. Okay, so this example, we have, say, 18 molecules. And we have 4 states. So each of the 18 can be is in one of 4 different states. And now let's say our macrostate looks something like this. So remember, the macrostate is N0, N1, N2, and so on. In this case, we only need 4 numbers because there's only 4 states that the molecules can be in. So this is the number of molecules in state 0, number in state 1, and so on. And let's say that, just for the sake of an example, that there's 3 molecules in the ground state, 6 in the first excited state, then 5, and then 4. Okay, so this is the macro state that we're going to calculate the multiplicity for. So how do we calculate the multiplicity? Well, that's basically like asking how many different ways can we arrange these 18 molecules into these 4 bins, so that there's 3 molecules in the first bin, 6 in the second, and so on. Okay. Okay, so the question is, how many microstates recreate this macrostate? That's what it means to find the multiplicity. So first, I want to talk about what is the total possible microstates for this system. Well, that's like asking which molecule, which 3 molecules go in this, which 6 molecules go in here, 5 in here, 4 in here. The total number of ways of ordering 18 molecules into these bins is, well, the first molecule, I have 18 choices. Now I choose the second molecule. In the second molecule, I'm down to 17 choices. And then for the next, I have 16 choices, and so on, all the way down until I have 2 and then 1 molecule left. And then I only have 1 choice about which molecule to pick. And so this we recognize as factorial, 18 factorial. So the total possible number of microstates is n factorial. Okay, but this is not the multiplicity, because we need to factor out the indistinguishable configurations. And what I mean by that is, if we have 3 molecules in this first energy state here, and let's say it's molecules 1, 2, and 3. Well, whether it's molecules 1, 2, and 3, or 2, 3, 1, or 3, 2, 1, and so on, the order doesn't matter. All that matters is how many molecules, or how many different ways are there of me picking 3 molecules for this first bin, if we disregard order. Okay, so here, order has not been disregarded. Here we've enumerated everything in order. And so now what we need to do is we need to factor out of this number the duplicities. So now we need to factor out the indistinguishable configurations. Okay, so I've rewritten the macro state here, 3654. And so let's look at this first bin. In the first bin, we have 3 molecules. And how many ways are there of ordering 3 things? Well, let me start with 3 marbles, say. I'm going to pick 1 marble. How many marbles do I have to choose from? I have 3. And now I choose a second marble. I have 2 to choose from. And then I only have 1 marble to choose from. So my total number of possible choices is 6, which we recognize as n naught factorial. It is the number of ways to arrange three things where order matters. So we want to factor this out because these are all indistinguishable configurations. All we care about is which three molecules are in the first bin, not what order they're in. So when we factor this out, what I mean by that is we're going to divide by this number. So now the number of distinguishable arrangements is down to 18 factorial, which is my total number, divided by the number of indistinguishable arrangements that I have because of the first bin. All right, let's repeat this for the second bin. So in the second bin, I have n naught as 6. Okay, so I have 6 factorial ways to arrange 6 things in order. And these are all distinguishable. So now my number of indistinguishable arrangements is down to what it was, 18 factorial over 3 factorial, but now I need to also divide by 6 factorial. Okay, and we repeat this for the third bin and the fourth bin, so you probably are seeing the pattern now, so etc. And so what is W? W, in this case, is 18 factorial over 3 factorial, 6 factorial, 5 factorial, 4 factorial. And if you plug these numbers into a calculator, you get that this is about 515 million different microstates that could account and recreate this macrostate. So 515 million ways to do that. And this is for a relatively small number of molecules. We're only talking about 18 molecules here. So imagine what this number turns into when we're dealing with Avogadro's number of molecules. So these numbers are gigantic, and we're going to address that very soon. Okay, so we computed multiplicity for a specific case, but what is it in the general case? So the multiplicity, or weight, of a configuration that looks like this, n naught, n1, n2. Remember, n naught is the number of molecules in state 0, which has energy epsilon 0. This is the number in state 1, and they each have energy epsilon 1, and so on. And by looking at the pattern we found up here, it's pretty clear that multiplicity for a configuration like this is going to be n factorial over n naught factorial times n1 factorial times n2 factorial, and so on, for however many bins we have, however many states we have in our system. Okay, so I mentioned that the multiplicity can be very large. For just only 18 molecules, we had 515 million different microstates for one particular macrostate. And so then the number's going to get much larger than this. So since W is so large, let's take the natural log. Okay, so when we take the natural log of a number, we're basically picking off the exponent, right? And so the natural log is going to greatly reduce the magnitude of the numbers that we're dealing with. Another advantage of taking a natural log, besides reducing the magnitude to more manageable numbers, is that we can make a nice approximation. So let's see that approximation. First, let me take the natural log of this multiplicity that we have here. Okay, so the natural log of this multiplicity is natural log of this. And now I'm going to use the property of logs. I have the natural log of n factorial in the numerator minus the natural log of the denominator, right? So this is minus the natural log of n naught factorial minus the natural log of n1 factorial minus, and so on. Okay, so I can write that as the natural log of n factorial minus the sum over I of the natural log of ni factorial. So notice in this formula, I have the natural log of a number factorial and the natural log of a number factorial. So this is one advantage of taking the natural log, is that we have an approximation for this. N factorial is a huge number, typically. And natural log is, this is the natural log of a very large number. And so we have an approximation that lets us calculate these large numbers fairly easily. And that's called Stirling's approximation. This is something you see quite a bit in statistical thermodynamics. And Stirling's approximation is just that the natural log of x factorial, and this is for large x, very large x, x much greater than 1, then this is approximately equal to x natural log x minus x. Okay, so this is a useful approximation. And what I'm going to do is I'm going to use it right here and right here and see what happens. Okay, so I've rewritten my expression for the multiplicity here. And so now let's use Stirling's approximation. So the natural log of n factorial using Stirling's approximation is n log n minus n. N log n minus n. And then inside this sum, I have the natural log of ni factorial. So that's going to be ni log ni minus ni. And that's all inside the sum. So looking at this term, we see that we have the sum of a sum. So we can separate that into the sum of two sums. The first sum looks like this. The second sum looks like this. Okay, so I just split this into the two sums here. And this we recognize. This is the sum over all of the number of molecules in each state. That's the total number of molecules, n. Okay, so this is n. And you see that this n, it's minus negative n. So this is a positive n, and that's going to cancel this negative n. All right, so incorporating those simplifications, I get something that looks like this. And so this is a slightly simplified version for calculating the multiplicity. Now, in the next video, what I'm going to do is I'm going to use these ideas that we've defined here, microstates, multiplicity, and so on, and I'm going to use that to derive the Boltzmann distribution. The Boltzmann distribution is probably the most fundamental, most important result from statistical thermodynamics. Everything is built upon that. So that'll be the topic of the next lecture.